All right, good morning, everyone. Thank you for coming. My name is Jonathan Buchholz. I'm the project manager for Sparta Robotics, and this is our preliminary design review presentation. So to meet our team, as I said, my name is Jonathan, I'm project manager. Emma is our documentation manager. Clayton Walker is our mechanical subsystem manager. Alexander Indritz is our outreach coordinator. Justin Maza is our electrical subsystem manager. Bruce Nelson is our software subsystem manager. Andrew Peterson is on our software team, and TJ Lilyblade is our deputy project manager. So today we'll be going over the general overview of our project, which includes the requirements that we've set forth to achieve, the concept of operations for how we are to enact our project, as well as a design overview for the mechanical, electrical, and software subsystems. We will have a mass and cost budget analysis, as well as a conclusion with a summary and question section. So for a brief overview, the project itself includes the design of 2 satellites and a robotic manipulator, the target satellite, which will be refueled, and the chase satellite, which will have manipulation capabilities. This manipulator is our system. So the main goal is that we have this manipulator mounted to this chase satellite, and it will be able to attach to, I'll go over the concept of operations later on, but the main goal of this project is that we will put forth good efforts toward minimizing space debris eventually in the future and increasing the longevity of the lives of satellites. So for the mechanical subsystem, this system is comprised of the physical structure of the robotic manipulator. This includes structure, links, joints, and an end-effector. The electrical subsystem comprises the electrical components of the system, which will be regulating the control of the system and ensuring we get proper sensor input. This is comprised of a control unit, as well as actuators and sensors. For our software subsystem, this is including our control algorithms and our computer vision capabilities to track a refueling port, as you can see in that picture. So for our concept of operations, this is broken down into 5 main steps. These include, sorry, there we go. Okay, so the first of these is the approach step. So the 2 satellites will be approaching each other, and when the chase is within reaching distance, approximately 45 centimeters from the target vehicle, we will be reaching out with our manipulator, grabbing onto a location on the target vehicle, which we will then actuate with our end-effector and grab the 2, pulling them together, docking them physically. Once docking is completed, we will then remove the manipulator from the grabbing port and reach to locate a central refueling port. Once we reach the refueling port, we will interact with it, refuel the target vehicle, and then once everything is done, we will release and then separate the 2 vehicles. Our list of requirements, we have 7 of them, the first of which is remaining within the budget. And then there's manipulation capabilities, autonomous operation, lightweight design, interfacing with the chase vehicle, properly grabbing and detaching from the target vehicle, and refueling the target vehicle. And now I'll hand it off to Emma to talk about our design methodology.
Thank you. So I'm going to go over a brief overview of our design flowchart. So we started off by ranking all of our requirements in order of importance, and then we used a weighted objective method to do this. From there, we decided to chose different design alternatives, and we used a morphological chart to show this. Then we did a design assessment using a utility matrix, and then we came to a design decision. So here is our overall weighted objective matrix. And we're going to use requirement 5, interfacing with the chase vehicle, as an example to demonstrate how we did this. So requirement 5 says the system shall interface with the chase vehicle. We started with requirement 1, staying within the budget, and we decided to decide which one was more important. Requirement 5 is less important than staying within the budget, so it got a 0 in the first block. Requirement 2 is also less important than requirement 5, so it also got a 0. Requirement 3, being autonomous, is more, requirement 5 is more important than being autonomous, so it got a 1 in our block. We did this for all the requirements and added all the 1s and 0s up to get a importance order of 4. From here, we use that for all of our requirements. Requirement 1 has the highest importance with a 6, and the budget is most important. The requirement 0 that has a score of 0 is being lightweight, being the least important. From there, we ranked all of our requirements in order of importance and then gave them importance scores ranging from 0 to 10. Budget, being the most important, got a score of 10, and then lightweight got a score of 4. From there, we added all the importance scores up, which gave us a number of 50, and then used that to calculate the weight by taking the importance score divided by the total importance. Here we have our morphological chart. Along the top, you can see our different options that we used. We came up with a maximum of 4 options with a minimum of 2. And then in the leftmost column, you can see all of the different criteria that we use, which are based on our components from each of our subsystems. Here you can see morphological chart 1. It is on page 3 of your handout. So for morphological chart 1, for our base design, we chose an inverse dome. For our actuator configuration, we chose a 6 DOF anthropomorphic arm, which means that it has 6 revolute joints. For our end effector, we chose a symmetrical grab end effector, and we have our material being aluminum for the base and ABS for the links and the end effector. For a microcontroller, we chose a NVIDIA Jetson. For our actuator type, we chose servos. For our camera configuration, we have 1 camera on the base and 1 camera on the end effector. For our camera type, we chose a USB 2. For our additional sensors, we chose haptic. For our refuel battery, we chose lithium ion. For our language, we chose C or C++. For our software environment, we chose embedded Linux. For our communication, we chose UART communication. And then for our control algorithm, we chose differential PID with forward feedback. You can see them being highlighted. So for design 2, it's very similar to design 1. Some of the major differences is that we have brushless motors instead of servos. And then instead of a lithium ion battery, we chose a nickel metal hydride. And instead of just using C or C++, we chose to use assembly with C++. Design 3 is very similar to design 1 and 2. One of the major differences here is that instead of using a dome or an inverse dome, we decided to use a box. And the actuator configuration has 5 revolute joints and 1 prismatic joint, which changes our amount of movement. We also, instead of using a symmetrical grab refueler, we decided to have a straight refueler for our end effector. So here we decided to use our subutility matrix. This is for requirement 5 using the previous example. We're going to focus on the microcontroller here, and so that we can explain how we scored each component. So for requirement 5, the requirement says that the system shall interface with the chase vehicle. The electrical requirements talk about communication between the system and the chase vehicle, and that they should interface through serial communication. The software requirements talk about how the software shall control the communication, and that it should communicate through serial communication with a protocol of 100 kbps. So for our microcontroller for design 1, we chose to use an NVIDIA Jetson. We gave it a score of 9. because it was excellent for our application and exceeded our specifications for this requirement and component. For design 2, we chose a Nook. We gave it a score of 4 because it has no onboard pin support, at which we could add using a USB, but it would not be the most convenient for our application. For design 3, we chose a Raspberry Pi. We gave it a score of 7 because it's simple to use, easy to implement, and it is a good solution to our design, but it doesn't exceed our expectations or our specifications. Okay. So here you can see that for our microcontroller, you can see our design 1 has a score of 9, our design 2 has a score of 4, and design 3 has a score of 7. When we chose the components for each requirement, we also gave them a weight as we did before previously. These can be found in our backup slides. So each different component has a different weight. Microcontroller has a score of 4.6. So how we got our utility score was we took our weight and multiplied it by our 9 for our score and got 0.414. Design 2 had 0.184 and design 3 had 0.322. We then added up all the utility and all the scores, and those are the numbers shown in bold along the bottom. From there, we took that and put it into our utility matrix. As you can see highlighted, they are the same numbers as the previous slide. We did this for all the different components for all the requirements, and then we added all of them up, which gave us our totals. So for our design 1, we have a total of 296. For design 2, we have 260. And for design 3, we have 263, which gave us utility scores of 7.874, 6.714, and 6.552. From there, we decided to use design 1 as it had the highest utility score. And now Clayton Walker will talk about our mechanical subsystem.
Hello everybody, I'm Clayton Walker. I'll be going over our mechanical subsystem for the design paths we have chosen. So, first off, we have our subsystem requirements and specifications for our mechanical subsystem. We took these into consideration when we were designing our first design path, and some of the more specific ones we will go through as we go through our presentation. Please refer to pages 1 and 2 in your handout. That'll give you everything you need to refer to as we go through. So, here we have our wonderful manipulator in its natural environment space. So we start out with our aluminum plate base. We use 2 aluminum plates because we want to make a modular system that attaches to the Chase satellite. The first plate on the bottom here attaches directly to the Chase satellite via these bolt holes here, here, and here on all of the corners of our system. This will allow us to attach to the Chase satellite, while these additional holes on the second plate here, here, and similarly placed on the other side of the system that you can't see right now, allow us to take off the top plate with our attached NVIDIA Jetson, so we can take it back to our lab and do testing on it and do whatever we need to do. When we actually do our testing on this Chase satellite, we attach it right back on and we're good to go. Inside our first gearbox here, we have a gearbox of a 3-to-1 ratio, and that is similar for both of our gearboxes 1 and 2. This is because the servo that we're using, which is the Dynamixel MX288AT, provides a torque of 2.5 Newton meters. This, while it does meet our specification, does not quite account for torque spikes, which are known to happen with these servos. So in order to account for that, we developed a 3-to-1 ratio for both of the first 2 joints. This allows us to account for that in the critical loading. And as we go further down our manipulator, we have less to consider. So we did not include a gearbox for those. Moving on, we have a joint bearing for each of our joints going through our entire manipulator. You can see it as this little gray ring in there. These are specialty ordered and designed for our system, so we have a complete supported system on each of our joints. This is important going forward, so we have a stable system for no matter where we are in our workspace. These joints are connected by linkages on both sides. They attach through the bearing and attach to the servo themselves, so we can attach them and provide any work or wiring that we need to do. They are hollow in the very center. You'll see that in our finite element analysis, so we can thread wires through if we need to. But we shouldn't need to. We have plenty of space and open design, so we can go on the inside or the outside. Next, we have our end effector. As said, is a symmetric open end effector, which means it is driven by one high-tech HS85MG servo. This will actuate a rack gear, which extends our refueling port right there, which will be a barrel plug. This extends all the way out when our manipulator is completely open, which opens to about 2 8 centimeters. We're grabbing a very small target. But for every other action that we're taking, it closes down and clamps onto where we're grabbing on the ring on this target satellite. But when we want to switch to our refueling function, we open it entirely, and we have a little port to attach where we need to refuel. This cuts down on the mass that we need to use because we only need one servo for our end effector, and it performs both tasks that we need. This also cut down on the need of using 2 manipulators. This allows us to use one for both tasks, which cuts down both on weight and complexity. We use a Logitech C525 camera. This provides a good field of view on our end effector and accuracy that we need to perform our software tasks, but I'll leave that to our software subsystem to describe further going forward. We also have a Logitech C920 camera on our base. This is so we don't have to utilize the Astro Team's camera that they're going to have mounted on the ceiling to do all of their tracking for both satellites. We have an entire system on our entire visual system on our system, so we have to not rely on any outside help. This also allows us to reacquire the target satellite should we move into a position where we can't see it with our end effector. This is more of a subroutine as opposed to a main task, because as software will explain, the end effector camera will do most of what we need. So going into the first gearbox, we got rid of the ABS shell so you can kind of see what's going on in here. It is driven by the Dynamixel servo again. This provides a torque of 2.5. We use a 3-to-1 gear ratio through this servo flange, which we'll machine out of aluminum. It connects to a steel shaft. We're using an 1/8 inch and a 3/16 inch. We use those because we can use them in both gearboxes. Because the way we order the gears, we can use them for both. The gears are attached by keyway and set screw. We can use either. We're probably going to use both for our design. And we have it set up as such. We have bearing supports on both sides to create a fully supported system. This is very important. As I said again, we want to have a very stable and reliable system for any task that we want to do. The top gear is, or the top shaft is also supported by 2 bearings. This is again for the same reason. We have the bevel gear, as I've said. We're ordering this from Boston Gears, which is a very reliable source, and we're at a 3-to-1 ratio. For our second gearbox, again, I got rid of the ABS shell around our whole gearbox here. These are brass gears. They are reliable. We've done some of the force calculations of those. We'll see them later in our finite element analysis, which I'll leave to my colleague Alex. So first, we're driven again by the Dynamixel servo, which provides the, again, 2.5 Newton-meter torque, which goes through, again, our servo flange that we're going to machine out of aluminum. These are the same for anywhere that we use them because of the same size shaft. So we have to, when we machine them, we need multiples of the same piece, which makes things much easier. The servo goes into the servo flange goes into the steel shaft, which goes again through our bearings. We want to make sure every gearbox and every joint that we make is fully supported no matter where it is. To that end, we have it fully supported on both sides with bearings. And then additionally, we have a bearing support on the far side because this is where we are actuating the very first joint in our actual arm. So we want to make sure we have a bearing on the other side so it doesn't tip and there's no play in it. It's a very supported system no matter where we are. So this is a standard linkage that we're using. We're using these for all of the linkages in our arm, except for the one that actuates our Z-axis. That one has to be designed differently because it only rotates about its own axis. That you will see later on in our design, or in our overall design. So again, we start with the same servo. Here's a Dynamixel servo again. We attach through a housing, which again is in 2 pieces. This allows us to assemble it more easily and have it supported on both sides by a bearing, which you can see there. These are special order bearings that are very thin, so they're a little bit more expensive, but they fit our task perfectly for what they are. So that's why we decided to stay with them. The linkage itself is made of ABS plastic. Anything in red you see in these CAD renderings is the ABS. Anything that's metal is reflected as such in its material choice. Going forward, we have our end effector here. That is the linkage you saw previously. That's kind of where it's connected to. We have our high-tech servo again. This actuates our refuel port underneath. It has an output shaft going underneath the servo there that connects to a rack gear that will extend it when we open, and then when we close, it retracts it back. And that also is driving all the gears to actuate every part of our end effector. Next, we have our camera, which we've mounted in a position where it can see our entire workspace, and in this position, we can do whatever the software system needs for us to do. Next, I'll hand it off to my colleague, Alexander Inlich, to go off over the torque calculations and our finite element analysis.
All right, everyone, thank you for coming. I'm Alexandra, and I'll be talking about our finite element analysis and also our torque calculations. So as I said, here are our torque calculations. We modeled each of the servos here and here as point masses, and then all of the servo housings and other components as a distributed load in W. All of our variables here are listed in the table, as well as their values, and then also a brief description of what those variables are. Adding up all of the distributed loads and point masses, we get a max normal force of 7.5 newtons, and gives us a max moment at the base of the manipulator of 2.6 newton meters. Putting that into our finite element analysis, our first component was the gear shafts that would be in one of the bases, gearboxes, shown here. And we use the loads from the bevel gears to get a tangential force of 48.2 newtons, a radial force of 5.6 newtons, an axial force of 16.6 newtons, and then the moment from the servo at 2.5 newtons, which gives a max yield in the shaft of 30.1 megapascals. But since it's a steel shaft, it has the yield strength of 370 megapascals, which gives a factor of safety of about 12, which is much greater than our specification of about 1.2 factor of safety. And it only has a max displacement of about 25 micrometers. Next element is the base plate, which has the max normal force of the 7.6 newtons, the moment of 2.7 newton meters, and then shown here in the arrows where the moment forces and also fixed supports were applied. Comes to a max yield of 2.7 megapascals, and yield strength of this aluminum plate is 125 megapascals, which gives us a factor of safety of 45.9, and max displacement of about 11 micrometers. Next element is the base link, shown here. Since this is the first link of the actual arm, this was pretty critical. So again, we have the max normal force of 7.6 newtons, moment of 2.7 newton meters, and comes to a max yield of 4.9 megapascals, and the yield strength of the ABS plastic that we got from our rapid prototyping lab is about 31 megapascals for the large filament used in the large Fortis printer, and that gives a factor of safety of 6.75, again, much greater than the 1.2 factor of safety required in our specifications. So it comes to a maximum displacement of 53.9 micrometers. Next element is the servo housings. So again, the same loads and moments applied again, since they will be at the base of the arm, so we wanted to use the maximum loads that they will be undergoing. That way, we are sure that they'll be used for each subsequent link, and comes to a max yield of 20.8 megapascals, which still less than the yield strength of 31 megapascals, and comes to a factor of safety of about 1.5. This is our lowest factor of safety, but still above the 1.2 required, and only has a max displacement of about 1.8 millimeters. Next is the rotator link. Same forces and moments as seen in the previous servo housing and other elements. Comes to a max yield of 17.215 megapascals, and the yield strength is still 31, so we have a factor of safety of 1.8, and max displacement of about 1 millimeter. So the end effector, the loads on this come from the total weight of the entire system, including the Astro's satellite, which is a total of about 11 kilograms, and we'll be moving at a speed of about 0.2 meters per second, so it gives us a force of 2.2 newtons. And the max yield on this says 3.5 megapascals, but that is actually a stress concentration. As seen here, there's a little bit of light at the fixed support. And so even with a number of fillets on that part, there was still a small stress concentration. So once we are able to figure out how to get rid of that, that number will go down drastically. And so it gives us a factor of safety of 8.8 and only max displacement of about 50 micrometers. And so that goes over pretty much all of the specifications. So as Clayton said, it consisted of one manipulator and has the 2 cameras. Both are less than 300 grams. And it also goes into provides the 3.53 newton meters of torque at the base with the 3-to-1 gear ratio. And the base is actually a 21 by 21 centimeter square, so it fits into that specification. Withstands the normal force of about 7.6 newtons. Also utilizes 6 degrees of freedom, no damage to the target vehicle. The ABS plastic that we were planning to use has a Fresnel hardness of less than 95, which is the aluminum for the grabbing port. And also interfaces with the refueling port and will have an accuracy of 1 centimeter. So it fits all of those, and then the other specifications will be talked about later on in the presentation. And I'll hand this off to Justin Mazza to talk about the trucks.
Thank you, Alexander. So first up will be an overview of the specifications and requirements of the electrical team. This will be gone over in our component section so that you may see how we complete all of our specifications and requirements. So first up is our circuit schematic for the entire manipulator. This shows all components and connections inside of the manipulator system. I would like to start here at the Chase satellite. This is where all of our power is going to come from because the battery is located inside of the Chase vehicle. And the other connections to the Chase satellite are going to be the ground, so that we have a common ground throughout our entire system, and 2 transmitting and receiving signals that go to our Jetson. So now from our Jetson, which is run at 12 volts, which is the power that comes out of our Chase satellite, the Jetson is going to have 2 cameras, here and here, the C525 and the C920, apologize. Both those cameras are going to be USB connected into our Jetson TK1. And then the Jetson, I apologize, is then going to be connected to our first servo and our PWM driver. So the reason that we have to have a PWM driver is because the PWMs interfere with our real-time application. And so we make sure that we have a PWM driver to go into our high-tech servo, which is at the very end of our end. This high-tech servo is then regulated down to 6 volts because it is much smaller than the other servos in the design. And if you go back to the Jetson, our first servo, the MX28, is going to be the only one connected directly to the Jetson. After that, the signal will be daisy-chained sequentially through the servos all the way to the end-effector. And that'll be at the 6th servo. And all these are connected to ground, which is connected back to the Chase satellite, ensuring that we have a common ground and there is no short throughout the system. Our next schematic is going to be over our refuel unit. This is our target satellite as we are unconnected. This is how it sits normally. So the target capacitor and the LED have linked cathodes so that the capacitor does not discharge into the LED at any point. And as we approach, we connect where those 2 switches are. And so that represents where we would be connected inside the circuit. Once those switches are closed, our battery is going to start charging the capacitor. And once that capacitor has reached relatively 80% charge, the LED will start illuminating. And once the capacitor has reached 100% charge, then the LED will be fully illuminated, and that will be received by our cameras, and we will understand that we are fully charged and we are ready to undock. So So the first component we're going over is our electrical connectors. We chose 22 gauge copper wire. We chose this because this fulfills our specification and requirement that we are able to connect components and have a maximum load of 3 amps. As you can see, the copper wire can actually carry 7 amps, so works perfectly for our situation, as well as being compatible with the pins on the NVIDIA Jetson. Our next component is our control unit and our PWM driver. We went with a NVIDIA Jetson because it satisfies our requirement that we are able to communicate with the chase vehicle, as well as we are able to use serial communication. On top of this, the NVIDIA Jetson is perfect for image processing, which we will use and will be gone over later on in the software subsystem. And then we used an end-effector servo driver, which is being referred to as the PWM driver, because, again, that helps with our real-time application. Next are our actuators. We have 2 actuators, the Dynamixel and the High-Tech. Dynamixel is significantly larger in torque power. There's a typo up there, but it's actually 2.5 Newton meters that we were able to output with the stall current of 1.4 amps. Then our second servo has a Newton meter output of 0.2, and that stall current is going to be 1.2 amps. Our next components are going to be our cameras. These cameras are the 525 and the 920. The one located at the end effector is this one here, which is the 525. This has a horizontal field of view of 61.4 degrees. And then our camera located at the base is this one here, which has a horizontal field of view of 78 degrees. Our next component is going to be our haptic sensors. We're using a 406 force sensitive resistor in this one. The reason that we decided to go with this is because these sensors can detect very small changes in force, as you can see in the graph here, which is taken directly off the data sheet from their website. And our last component is going to be the battery that we use to refuel the target satellite. This battery is a 3.7 volt with 6,000 milliamp hour battery. It completes our specification of having 3 kilojoules or more of energy storage. This is to propel the circuit forward so that we may actually continue charging throughout. And next is going to be our specification completion. So you can see all the specifications in slide 1 and 2 or on your paper that are now completed throughout our component section. And next is going to be Bruce Nelson talking about the software.
Alright, thank you very much, Justin. So this is a brief overview of our software subsystem required specifications. You can go ahead and look at them on your handout if you have one on slides 1 and 2. Briefly, the software subsystem is broken up into 3 main components. First one being machine vision for detecting the target satellite. The second one is the control algorithms and the manipulation capabilities, which assists of bringing the robotic manipulator over to the target vehicle. The third one's going to be the real-time aspect of operating real-time determinism to our system itself. So we'll examine these over in our software flowchart. For those that have it, you can refer to page 7. Should be page 6 on your handout as well. So this is a control flow process of our software throughout the entire mission objective. So with that, what it will be doing is previously, before we'll start the process, is the chase satellite will be bringing us to the target satellite. So once we are in proximity of that, we'll be getting a signal. So we'll be getting a signal received. So we'll check, okay, are we close enough from the chase satellite? So the chase will pull that data to us, and once we're close enough, then we can actually start the grappling process of attaching to the target satellite. So over here, we'll see if we can align to a docking ring. So how that will work, it will detect the docking ring, which we know is a known object. It will then see if we can track it. Now, if it's the first time, we can't track it, so we'll have to detect the docking ring. So once that's detected, then we can go ahead and start tracking the object. It will then send those coordinates that it obtained into Cartesian distance coordinates. That will go into a kinematic model, which will translate that to servo movement. That will repeat the cycle until the manipulator is within range of the docking ring in order to be able to grapple onto that. So once that is close enough, it will be able to grapple onto that ring. Next, that will bring us to a process of docking the two satellites together. The chase satellite over the target satellite. So how that will work is we'll slowly pull the chase satellite towards the target satellite. We'll pull for a signal from the chase satellite saying, okay, are you docked? Are you docked? Once it receives the signal from the magnetic plates that it gets a charge that it is docked, we'll then proceed with the refueling process. So that is a similar process as far as detecting the docking ring, but this is optimized for the refueling port. So same concept, we'll be detecting the refueling port itself. Once we detect it, we'll be able to actually track it. It will then translate a Cartesian coordinate distance to the kinematic model in order to translate it to distances for the servo movement. Once that it is range of directly above the refueling port, it will then insert the refueling apparatus into the connector onto the target satellite. Now, once that is connected, we can actually start the refueling process. So the refueling process will start, we're charging a capacitor, so it will keep refueling and it keeps checking, okay, are you charged yet? Are you charged yet? Once we receive the signal that the target satellite has been refueled, our mission has been completed, we can reset the arm, and then we can power off the system. And this marks a mission success and that we've completed our mission objectives. So here's just a preliminary design of our tracking and detecting of a refueling port. So we're using a detection and tracking of a single object. We know it's a known object. And what this is showing, we're keeping the object itself within the bounding box, and then we're computing the distances on the x, y, and Cartesian coordinates, and also the z coordinate as well, as far as distance from the camera to the target as well. So those techniques will be explained on this slide. So for this, we decided to use C++. It's a fairly common and robust language for embedded systems, and especially for real-time applications as well. We also decided to use OpenCV for our machine vision applications, which support the detection and tracking algorithms we decided to use. We'll also be using POSIX libraries to simulate threading capabilities in order to achieve our real-time requirements. Now, for the detection and tracking, they work pretty much together. We're actually using a single object and tracking algorithm since we know the object itself. The detection we're using is Hard Cascades. It's worked on detecting edge-like features. Something like a face has your eyebrows, your nose, your eyes, and your mouth. They're unique features, and since the refueling port will have a unique pattern on it, we'll be able to recognize that. So what's nice about Hard Cascades is although it has a long training time, we don't have to train on the satellite. So we can insert the data set, and it's actually fairly quick. In an example, we ran at 30 FPS. It was able to detect it at each frame. Now, we combined this with the tracking algorithm because the detection is fairly slow. It tries to detect every pixel and compare it to the object at hand. With the tracking, you're using the circumference matrix, so you're getting low calculation speed, and you're only comparing it to the neighboring pixels. So you can predict where it's going next, and you know the general direction. Now, for the distance, as far as finding the distance, we are not using stereoscopic. We're actually using one camera. The two cameras we have, they'll be able to switch off in order to detect and track the object. But most of the work will actually be done on the end-effector camera using triangle similarity. So how this works is because we know the known object, we know the dimensions, and let's say we're at 600 millimeters away, we know it's size 200 by 200. Then we compare the dimensions of that object when we're closer away, 500 or even farther. And then we also take those pictures, images of it at different angles. From there, we create a lookup table, and we use it as a hash in our code in order to reference it when it's within that specific data set. So with that, it's very computational and inexpensive because it's using geometric principles, and we don't have to use two cameras. It's less load on the electrical subsystem because we only have to use one camera at a time, and it's less expensive as far as the system load on the Jetson itself. So I will go ahead and pass this over to Andrew Peterson, who will go over our kinetic algorithm and our control algorithms.
Thank you, Bruce. As Bruce mentioned, I will be talking about the control algorithm that we implemented for our manipulator. So first, for any robotic manipulator, it is imperative that we solve a forward kinematic. This is begun by creating a definite Hardenberg table, which consists of the geometry of the manipulator, in particular the joint angles and the link lengths. This is a simulation of our manipulator reaching a current desired joint angle orientation. This is done through the implementation of an inverse kinematic, which basically does the opposite of the forward kinematic in that it receives a current pose consisting of a position and orientation and gives us a desired joint angle vector. Next, we have to calculate the torques for each joint. We start by calculating an overall torque of the manipulator as a whole. We then decentralize the torque, meaning we solve for the torque of each link individually. That is then set equal to the PID compensation torque of the system, simplified to this TI equation here. And we take the derivative of that equation, giving us a third order ordinary differential equation, which is then used in the ODE 45 solver in MATLAB. So some important matrices that we use for those torque calculations are the B, C, and G matrices. First is the B, or mass matrix, which is dependent on joint masses as well as Q, which is the current joint angle for the manipulator. Next is the C, or Coriolis matrix, which simulates the velocity acting on the system, which is it takes into account joint angles and velocity. Last is the G matrix, or the gravity matrix, which simulates the gravity that will be acting on each one of the links of the manipulator. This is a block diagram, which you can see on page 7 of your handout. In the top left, the desired joint velocity and acceleration is input to a friction and the B hat term, which is combined with gravity to give us a feed-forward torque of the system. In the bottom left, you'll see that the desired joint angle is input to the gains of the PID compensator, giving us the PID torque of the system. These two torques are combined to give us our current joint angles, velocity, and accelerations. This is a simulation of the compensator in action. As you can see on the right, the joint angles approach their desired orientation. The maximum percent overshoot for the system was calculated to be 2.7%. Maximum settling time was 1.6 seconds. And the maximum torque in the simulation came out to be 3.48 millimeters. As you can see, we met most of our software specifications for this project. The few that we did not meet are because we currently do not have the hardware to perform necessary testing in this point of the preliminary design stage. I will now hand it off to TJ Lilyblade, who will tell you about our mass and cost budgets.
Thank you, Andrew. So, we will begin with the mechanical mass budget. The largest item that we have is the 2 aluminum plates that make up our base, totaling a mass of 1.099 kilograms. This is followed by the ABS filament. We expect to use 0.182 kilograms of that when constructing the joint houses and links. Adding up all of the other assorted rods, gears, and bearings that we expect to use, we believe the mechanical subsystem will have a total weight of 1.554 kilograms. The electrical mass starts with the servos as our largest part, weighing 0.432 kilograms for the 6 large servos, followed by the Jetson and the Logitech C920 camera as our next heaviest pieces, all on the base. Coming up with a total weight of 1.144 kilograms for all electrical parts when added together. This does include an estimation of using all of our wiring, so this is probably an overestimation in this part. Adding these together, we come up with a total system mass of 2.698 kilograms, which, as you can see, comes well under budget for both of our specifications, of the mechanical system weighing less than 3 kilograms and the electrical system weighing less than 5 kilograms. Moving on to the cost budget, the largest cost for the mechanical systems will be 2 spools of the ABS printing filament at $59.16, followed by the 3 specialty thin bearings, having a quote of $50 for those. Adding together all of the other rods, gears, and other bearings, we expect to pay $363 for the mechanical portion of this project. The electrical costs, the largest cost would be our dynamical servos, but those were graciously donated, meaning that our highest cost item will be our NVIDIA Jetson at $149.32, followed by our cameras at $67.79 and $44.79. We expect to pay a total of $377 for the electrical portion of this system. Adding these together, we come up with a total budget of $740.28 for the full system, which comes in under budget for both of our specifications. Again, $600 for the mechanical subsystem and $500 for the electrical subsystem. I will now hand it back to John for our summary and conclusion.
Thank you, TJ. So, to summarize, we've gone over our main project goals and concept operations, as well as our design methodology for developing our final path design. We've presented analysis of each of our individual subsystems, as well as analysis of the cost and mass budgets of the system. Here are our references. And for acknowledgements, we'd like to recognize Dr. Gentilini for supporting our project, as well as Professor Richard Mangum, Dr. Julio Benavides, Ernest Stokesbury, Dr. James Weber, Dr. Sam Seward, and Dr. Brian Davis.
PhD.
Thank you for your time.
PhD.
Are there any questions?
So first question is about space.
Temperature requirements in space.
Right.
Did I see a temperature requirement?
So we are doing a proof of concept of this because it's a study that NASA's doing at the moment. This is not a system that's actually going into space, so as such, we did not put that in as a requirement.
ABS. I have serious concerns about the strength of ABS, especially when it's 3D printed, and whether that's going to be adequate, and thinking about creep and fatigue. Is there a durability requirement for the robot? How many cycles does it need to survive?
All right, so the numbers that we got were actually given to us from the rapid prototyping lab, the filament that they use in their larger, not the smaller MakerBots, but the larger kind of Fortis machines, and so the only kind of durability requirement is that the Astros have a time limit of about 15 minutes, and so it needs to withstand that as well as some other testing, but we don't actually have a specification saying how durable it needs to be.
And so can you speak to the strength of ABS after it's 3D printed? Have you done any experiments on any of the parts or figured out what the actual strength is versus the filament strength?
So the rubber prototyping lab has some, but they didn't have any like actual numbers to give us. They said that most of it depends on how it was printed. Can't really speak to how strong it will be before that though.
So that is another reason we bought 2 spools of ABS. We are planning on the fact that we're going to build a number of each of these components and we can do testing for these sorts of things on them. Our final design may differ from this slightly based on that testing, but we haven't ordered any of our components as of yet. But when we do, testing is definitely part of our process.
The aluminum base came out the highest weight item. Have you considered hollowing that out so that, do you need to have a solid base?
Not necessarily a solid base, but as you, TJ described, we are way under budget for both mass and costs, so we believe that using the 3/4 inch aluminum sheet is still 3/16. Is still a valid cost.
Thank you.
All right, just a couple of questions on electrical. So the servos, if you could go to the schematic with the servos, you talked about them being daisy chained. So you've got one PWM signal going into one of them, and then they're all receiving the same PWM, or how does that work?
So they operate with TTL communication instead, and so there's going to be feedback from every servo, which will progress sequentially all the way back to the Jetson, and using that feedback we're going to determine where we are and where we're going.
So TTL, you mean serial?
Yes.
Serial, okay. Okay, that makes more sense. And then second question on the circuit you showed with the capacitor and the couple of resistors in there when you connect it up. Okay, so this is, you've got batteries, those are on your arm, and then the other side is supposed to be what's on the other satellite that you're recharging, is that correct?
Correct, sir.
How did you size those resistors?
So I just took a small value because we're using the 0.1, and then when I end up calculating the circuit, we end up coming out with about 10 seconds of charging time. And so the resistors limited the spike current in our schematic, and they work. So.
Okay, so how do you calculate out how long it's going to take for that capacitor to charge?
We needed the, forgot the other letter, but the constant of the capacitor.
Time constant.
Yes. And so that time constant is 10. And so then using that, we were able to calculate how much time it would take.
And what voltage are you trying to get that capacitor up to?
I didn't calculate for voltage, I calculated for reaching full charge.
Okay, but what do you mean by full charge? Because you got a voltage divider there. Your 2 resistors are going to split voltage. You got an LED in there, so you're going to have slightly more than 50% of that battery voltage.
Yes, sir. I split the voltage there so that I could get the LED to illuminate slower. That was the only purpose of the secondary resistor.
Okay, but are you charging up to 3.7 volts, or what are you trying to charge up to for that capacitor?
So I never calculated that, so I don't know, sir.
Okay, so what is your goal of how much voltage you want to have on that capacitor in order to view the other satellite as being charged?
I don't know yet, sir. I'd have to calculate that.
So you'll have to look into that. So is that capacitor representing a battery bank, or what do you?
No, it is a 0.1 farad, just a little capacitor.
Okay. All right, so just recognize you got a voltage divider in there. You're not going to get your full voltage. You got to figure out how much voltage is actually charged, and then do some calculations off of that. At least you got a current limiting resistor in there for your capacitor, so you aren't going to damage the batteries. Now the battery on the other side, so that's on your arm. How does that recharge?
That it is the little blue battery that you saw in the component.
Yeah.
So it has a compartment on the base that we'll just plug it into and take it out of. So it's really easy for the battery itself to move. And then when we buy that component, it comes with a charger because it's a lithium-ion battery.
Okay, so you're out in space, right? And so you charge up one satellite, and then your batteries are drained. Are you going to recharge it, or are you just one shot and done?
For our proof of concept, it's one shot and done.
Okay.
And for any space aspect, I assume we would go for some solar charging.
Okay. Thank you.
On chart 26, you alluded to a vision system on satellite that said that you wanted to have your own independent vision system. Do your requirements require that you have that independent vision system, or is it a nice to have?
It was mainly a nice to have. We're interfacing with the Astro team, so they'll have a camera, an overhead camera over above that will pretty much help the two satellites get into close proximity. But for us, we needed the two extra cameras on our own manipulator for accuracy and precision when docking onto the test target satellite. And as far as refueling, because of the camera on the end effector, we really can't do that with overhead camera because of the amount of pixels and accuracy. So we'll need something on the end effector which is closer, and it will help with the manipulator capabilities as well as controlling that and navigating it to the refueling port.
Okay, yeah, I think that in the presentation we should be clear on what's a requirement and what is not, because it came across as we're just adding it and adding cost and weight without really needing it, whereas in reality you're telling me that if there's a requirement that what was available on the satellite did not meet the requirements you need. So be clear there. On the budget presentation, I encourage you to be careful with significant figures. So when you're talking these sorts of dollars, there's no need to talk about pennies. And then I'm going to, not because I want to pick on Alexandra, but my background is more in stress and thermal, so a little bit on the language. When we speak of what's coming out of the finite element analysis is not max yield, but stress. It's an applied stress that we'd be comparing against an allowable strength. And this gets to what Dr. Choles was speaking to. On the ABS plastic, it is real important that you understand what your allowable strength is. And so I encourage you, as you alluded to earlier, to do some mechanical testing, and not making the components and testing those, but rather make some dog bones and get actual strength properties to compare with. And the margins you were computing were very large, which that's a good thing. However, if you're 3D printing, you should be taking advantage of that and reduce the weight. Yes, I'm not sure where your weight and cost budgets came from, but if you're going on a satellite, you want to be as light as possible. And so none of the requirements here do not require any space operation at all. So you're building a proof of concept principle, so all space operation requirements are off the table. Is that correct? Thank you.
Okay, on slide 27 and 28. So you're manufacturing your own gearbox, is that correct?
Yes, that is correct.
Okay, and that's at the very beginning of your kinematic chain.
Yes, that is the first joint.
Okay, so any kind of slop in your gearbox is going to be amplified by the distance out to the end effector.
Right.
So that's very critical to get those tolerances tight, or else you're going to have a lot of play and inaccuracy in the position of your effector. One thing I would have liked to have seen, and you have this in your morphological chart, but no real big pictures of it is the schematic diagram for your manipulator and why you chose the particular configuration that you selected. There's just little thumbnail images, and I can't really see those very well. Yeah. And you can kind of make it out from the CAD drawing, but it would have been nice to have seen the schematic as well. Let's see. Yeah, that's better. A little bit better. Okay. Slide 45. And this is just nitpicky stuff right now. Maybe it's not 45. The one with your wire. Maybe it was the previous slide. Are you using solid or stranded wire?
Solid.
Solid, and this is going through the manipulator all the way to the different servos and
What do you mean by through?
starting from your microcontroller out to the devices, the actuators.
And there will only be two wires connected between each manipulator.
Okay, but that has to run the length of your arm. And if that's solid wire, you're bending it constantly.
Oh, well, we connect into one part of our servos, and then it's a whole different wire. I apologize.
Okay.
So we connect into one part of the servo, snip the wire, and then we connect on another side.
Okay, so that wire will never bend when the arm is moving. Is that
It will be with the link,
okay?
so it's not going to bend like other than how we bend it with the link. It
Okay.
will stay rigid.
It's fixed with respect to the link.
Yes.
Okay. Okay, then solid should be fine. How are you solving the inverse kinematics problem? What technique are you using?
So that was basically derived from the forward kinematic. The forward kinematic is, what that does is it takes into account the joint angles, and that gives us a pose, which is the X, Y, and Z position, as well as phi, theta, psi, which is an orientation, so the angle of the end effector. So what we do is we put that into the forward kinematic, and what that does is it allows us, basically doing the inverse of forward kinematic, to get the desired, it gets us back to the desired joint angles.
Okay, so you're solving it numerically? You don't necessarily have to be analytical solution, but a numerical technique?
No, the method was a differential method.
Okay.
So no, we attempted a numerical and that did not work out. So
Okay. You attempted an analytical and that did not.
analytical, yes, you're
Yes,
right.
okay.
Yes, sorry.
Okay, how many iterations do you have to go through to get a solution?
The number was around 40.
40? Okay, and you can do that fast enough?
Absolutely, yes.
Slide 62, this is just the last thing I have. You have performance measures, but how will those performance measures change once you have grasped onto the other satellite?
We had not taken that into account.
Okay, because your dynamics model is going to completely change once you grasp onto the object. And that's going to also change your performance measures, because your controller is designed for a nominal system without that. So. But other than that, good job.
Thank you.
Morning, all. Keep it short and sweet. So top level, I saw that you provided a lot of functional requirements which seem to have connectivity to some sort of performance requirements, correct? I would suggest that there may be a few top level, specifically performance requirements, such as what Dr. Eisenberg touched on just a moment ago. When I'm using the arm, do I have a definite performance requirement for the position repeatability that I have to be able to place the tool at, and also orientation? That flows back into my controller, which you talked about on slide 62. And if I can go to 60 just for a sec. The question was asked earlier, this is something that you're building for space, but I'm only going to use it here on Earth. So it left me scratching my head. What's G?
G is the gravity vector that we're using for testing purposes when we're in.
So you're going to be using the G on the ground?
Yes.
Because that dramatically changes a lot of your calculations, obviously. It's good in some cases and not so good in others. So you're going to be using G on the ground. Okay, fine. So your performance of the controller, again, as I said, should flow down from some position and orientation performance specs of the top level problem, and that's only going to be part of it because your flex, the repeatability, if you will, just of the arm itself and the flex in it, that will also cause some errors, even if your controller is perfect, the weight loading and deformation. So you might seriously want to go back and ask, what are the performance specs even for the controller, rather than saying, I implemented something and here are the specs I saw. Usually we work the other way around. We say, here are the specs that I want to meet. Now I use that to drive the choice of my controller, and the performance parameters come from it. Does that make sense? Or did you do that? Or did I miss something?
So our specification,
So the main specification I think you're talking about was we chose to meet a 5% overshoot or less, as well as a settling time of less than 2 seconds. And so that went into the consideration of how we chose the PID controller. And then, as you saw on my last slide, the percent overshoot and settling time were within those specifications.
Is that meaningful as a percentage overshoot when I'm talking about smacking the thing I'm trying to contact? Isn't there some sort of absolute metric that I flow backwards? These are nice, convenient things to say, things like 5% overshoot, but doesn't it tie back to some physical distance? If I whack the mating surface and go through it by 2 centimeters, that might be a problem. Follow where I'm going?
Yes, sir. Yes, so the plot actually represents those distances in the joint angles. So that's how the percent overshoot was calculated, is it has the joint angles going to a specified angle, and based on how far past that angle it went before it settled, that was how we determined our percent overshoot.
You might want to go back and revisit some of those concepts. And in the end, is it really only a positional specification? Do you not care about detecting the orientation when I'm using the image processing algorithm? Do I not care about both? Whoever was doing the image processing. When I'm looking at the mating rings, I care not only about how far I am away from it, do I not care about the orientation of the ring also?
We also
Rhetorically hopeful.
Yes, we do care about the orientation. As far as solving that in the image processing concept, is since we're using single object detection, is capturing different angles of the object. So we know that we can only grapple at one angle though, rather than on the side. So we'll be accounting that, and we'll be analyzing those, making an algorithm that, okay, we can grapple at this angle, orientation versus this one. So we'll look at the table to determine which parameters we'll be able to actually grapple onto for the document.
Maybe we'll talk.
Okay.
Go to slide 61, please. In this picture, you have a derivative block. Are you actually intending on taking the derivative of those signals?
Yes, sir. So what we did was in our ODE45 function, the function we had that call, it doesn't per se take the derivative. We made a separate equation, which was a derivative of the error between where we currently are and where we need to be. So we have an equation for the error, and we took the equation of that and hard-coded that into our control function.
Okay, we can talk more about that later. Just a couple general comments. When you presented like slides, go to like slide 17, for example. When you talked about your different designs, you had these nice charts of, okay, for each thing I have 4 different options, and this is design 1, this is design 2, this is design 3. I didn't get any sense of why you chose like these particular things for design 1 and a different set for design 2. Could you talk to that a little bit? I know you're time limited, but it was, I'm assuming you didn't just randomly throw darts and go, oh, we'll do this one, this one, this one, and this one. So I'd like a little bit of the rationale behind the different design choices, please.
That was a very good question. So we chose things that we would all think that would work together. When we were choosing our individual components, we looked at a very broad spectrum of things that would actually meet what we needed. And then from there, we chose things that we thought would work the best. And then when we looked at our different utility matrices with the different scores that we gave each component, we reevaluated what our decisions were and making sure that all of our decisions were the best for what we needed.
Thank you. I assume there was a lot of work that went into that, but it was not mentioned at all, so I just wanted to bring that up.
All right, yeah, I do believe we are out of time, but thank you.